Hello, everyone. Let me thank the organizers again for the invitation. It is my great pleasure to be here today and discuss our recent research on the more interest with constraints. This is joint work with the Tangzhou. So the talk gonna be divided into several videos. In the first video here, we discuss the motivation, why we care about this topic. And in later videos, we discuss an abstract formulation to answer a very fundamental question about this topic, and then we applied it to study capillary surfaces. So let's start with the motivation. So one consider several optimization problems in geometry, and here is an example. In the image here is about the legend of Princess Dido. So according to the legend, Princess Dido and her people fled to North Africa. They gave the local king their valuables, and in exchange, the local king agreed to let her take as much land as she could enclosed by an offside. So Princess Dido was a very good, very smart mathematician. She decided to cut the oxide into very thin strips, knot them together into a long rope, and use it to enclose a very large piece of land upon which the city of Carthage was founded. So, as you can see in the picture, um, Princess Dido and her people cutting the oxide into thin strips. So this is an example of an isoperimetric problem. That is, Princess Dido would like to find the maximal uh, she would like to find the maximal area way to be enclosed by a given perimeter. So maximizing area given a perimeter. Equivalently, you could find the least perimeter ways to enclose a given volume. This is equivalent to uh, minimizing the perimeter given the area. Now, let's solve this is a very classical, very well-known problem in geometry and in mathematics. So let's consider another optimization problem of partitioning a convex body. So let me draw a picture here. So here omega here is a convex body, and now sigma here is a hypersurface dividing omega into two portions, and each portion here has certain volume. Let's call it let's call them V1 and V2. So they all depend on sigma. Furthermore, sigma here also divides the boundary of omega into two portions, and then we can compute the area of these two portions, which also depend on the hypersurface, the partitioning surface sigma. So they are called the wetting area. So we have W1 mega. So this is the wetting area. And let me use another color to illustrate the wetting area. So the wetting area is the area of the portion of the boundary of omega divided, determined by sigma. So here we can consider several optimization problems. That is, we can consider the least area way to partition a convex body. So mean area of sigma with prescribed volume given a sigma, or with prescribed wetting area, or both. Okay, so that's why there are different optimization problems to consider. Furthermore, using the Lagrange multiplier, we can consider the problem of minimizing the combination area of sigma minus lambda W of the wetting area given the volume. So lambda here is the Lagrange multiplier. So this formulation will be important in the later part of the talk when we discuss capillary surfaces. So these are examples of optimization problems in geometry. So the standard approach to these problems is given by the theory of calculus of variation. So in the theory of calculus of variation, we consider a functional, and let's call it A, and A here can stand for either area, volume, energy, or some combination. Then we consider all admissible deformation that can happen. And for hypersurface, for two-sided hypersurface embedded in an Euclidean space, then a deformation is totally determined by its velocity v, and the velocity v here can be identified as multiplication of some function u with a choice of the normal vector to the hypersurface. So, and here is a choice of a normal vector to sigma, and u here is just a function on sigma. So a deformation is identified with a function, with a smooth function on sigma. Then generalizing derivative test from calculus, one can compute the first and second derivative, which are called the first and second variation. And when you compute the first variation, you obtain some formula. And if you let that first variation to be equal to 0 for all possible deformation, then this leads to critical point. So critical points are candidates to be the solution to the optimization problems, but at this moment, we don't know which one is the solution. That's why it is important to compute the second derivative of the functional. But the second derivative of functional here is a little bit sophisticated. Recall that we consider a functional which depends on all admissible deformation, and each deformation is identified with a function on sigma. So the second derivative here actually that's gonna be associated with an operator that acts on this space of deformation, and this space of deformation is identified with a space of function. So this is an operator in a space of function, and so this operator is actually very nice. It's normally symmetric and also continuous. So we can, if we understand this operator, that's equivalent to understand the second derivative test in calculus. So this is actually the starting point of what we call the index theory. So from calculus, we know that stability is equivalent to a local minimum, and here in this situation, in the calculus variation, this is equivalent to the case when the second variation is positive definite. So the operator that we mentioned earlier is positive definite. So thinking about this operator as a matrix which acts in a infinitely dimensional vector space. So stability is equivalent to a positive definite matrix. Then it is natural to define the stability index, which is also called the Morse index, which is the number of distinct ways to decrease the functional to second order. So in other words, this is exactly maximal dimension of a space on which, so let's call this operator here, let's call this operator Q. So maximum dimension on which this Q operator is negative. Definitely. So basically, the more index counts the number of deformation that decrease the functional to a second order. And this notion has been developed by Edwards, Smale, Simons, Hestenes, and many other mathematicians in the last century or so. Now, the index is actually a quantitative measure. So index equals 0 here, that is equivalent to the stable case. And as we saw earlier, this is equivalent to a local minimum. However, we can make further observation about the index. One general principle is that the lower index corresponds to a higher symmetry. And the reasoning is follows. In reality, symmetry is associated with efficiency. That is, optimal configuration to optimization problems in reality normally possess a lot of symmetry. So if you have a configuration with low index, then it's not the optimal solution, but it is close to the optimal solution because it is relatively difficult to decrease the function of the second order for that configuration. Low index means probably there are only 2 or 3 different ways to decrease the function of the second order. Very, relatively difficult. That's why even though it doesn't possess the optimal symmetry, it must possess certain symmetry. So that's why the lower the index, the higher the symmetry. And these viewpoints actually, so using these viewpoints, we can using these viewpoints, the index gives a natural hierarchy for the set of critical points. So this perspective has been developed to great effect in recent years by the work of Marquez and Neves, solving the Wilmot architecture, Tristan Riviere, Sinjo, and other mathematicians. Now let's discuss the notion of constraint. So constraints are the mathematical modeling of limited resources. For example, as we saw at the beginning of the talk, Princess Dido would like to enclose as much land as possible, but she only had a finite strip of finite length because it was given outside, and she cut the outside into thin strips and knotted them together. But eventually, is that is finite. Then, so the limited resource here is the finite fixed perimeter. So remember, the isoperimetric problem is to find the most area way to be enclosed by a fixed perimeter. So that is an example of a constraint. So how does that affect our understanding of the index? It certainly create challenge to understanding of the problem because we are led to consider a smaller space of information. On a critical point, only deformation preserving the constraint are admissible. That's why we have a smaller space of deformation and smaller space of deformation. And recall that a deformation is corresponding to a function. So when we consider a smaller space of deformation, that equivalent to a smaller function space. So the fundamental question here is, how does the Moore index change under constraint? That is, we had the Moore index with respect to O smooth function. Because of the constraint, we are led to consider a smaller function space. So now we had to compute the more index with respect to a subspace, this function space. So how does it change? That's going to be the main question we're trying to address in this talk. So first, let's revisit the problem of partitioning of a convex body and see how the constraints appear in this problem. So for simplicity, when think of the convex body as an Euclidean ball, and as we saw earlier, there are two different types of constraint. So the type 1 is corresponding to fixing the enclosed volume, and we can show that this is equivalent to consider a smaller function space, and here the smaller function space must satisfy the condition the integration over sigma of u must be equal to 0. Then the type 1 constraint is corresponding to the case. The type 1 constraint is corresponding to fixing the wedging area, and similarly, this is corresponding to a smaller function space, and here the smaller function space is characterized by the equation the average, the boundary average of u must be equal to 0. So the type 1 more index in this case is index of the operator q, but now we only consider the subspace. Let's call the subspace here the subspace of function satisfying this integral condition, integration of u over sigma equal to 0. And the type 2 more index is again the index of the same operator, but restricted to a different subspace, the space of function with the space of function satisfying the integration over the boundary of sigma equal to 0. So hopefully at this point you see why it is important to study index with constraint and the exact question that we're trying to address here in this talk. So how do we answer that question? That will come in the next video.